Hi, and welcome again to my Physics Online video lecture series. Today's video, I'm going to be talking about the second law of thermodynamics, and I'm going to do it via three different statements that are all actually equivalent to each other, that are different ways of stating this second law of thermodynamics. In order to really understand what's going on, we have to consider how a heat engine works and or how a refrigerator works. And to do that, I'm going to kind of draw in different colors here. Essentially, in both cases, whether it's a heat engine or whether it's a refrigerator, we have two reservoirs. One is a hot reservoir, one's a cold reservoir. So this is the cold reservoir, this is the hot reservoir. Now, for a heat engine, essentially what happens is we draw some amount of heat out of this hot reservoir. That amount of heat we might represent as QH. This then splits into sort of two things. One of them is that we are able to do work, so work. And the other is that we transfer some of this heat into the cold reservoir. So we could call that QC. And in some sense, there is a rejection of some of this heat from the cold reservoir. And that is equivalent to how much work can be done. So the work in this system, let's go ahead and write it back in black. Let's say the work done is the QH plus QC, where QC is negative. So we could write this as the amount of heat from hot minus the amount of heat rejected. Or minus the amount of heat pulled into the cold. So this is how much work is being done by this heat engine. So this diagram represents a heat engine. The diagram, in some sense, taken in reverse, is how a refrigerator, or for that matter, an air conditioner works. So we have our hot reservoir again, we have our cold reservoir again. So cold down here, hot up here. And this time, we basically are able to pull some heat up from the cold reservoir. We'll say Q cold. And this time, instead of doing work out of the system, we have to kind of do work into the system. Work in. And the result of this work is that we're able to pull this heat from the cold reservoir and dump it into the hot reservoir, QH. And this time we might say that the work done, work in, plus QC is equal to QH, how much heat we've sort of shunted into the hot reservoir. So you're basically pulling heat out of the cold reservoir, putting it into the hot reservoir by doing some amount of work on the system. So this is basically your refrigerator, or alternatively your air conditioner. And again, this is a heat engine working in reverse. So what does the second law of thermodynamics say about this pair of systems? Well, there is the engine statement. The engine statement says that we cannot basically convert all of the heat pulled from the hot into work. Now, the specific statement is that we cannot, or that it is impossible for any heat engine to undergo a cyclic process in which it absorbs heat from a reservoir at a single temperature and converts the heat completely into mechanical work. But this is a good summary of that law. There's also the refrigerator statement. So the refrigerator statement, again, of this second law, says that instead of doing work, we want to know, can we cool a system without doing work? And the answer is no, not spontaneously. Essentially, this could be stated as, it is impossible for any process to have as its sole result the transfer of heat from a cooler to a hotter object. In other words, in order to transfer heat from a cold reservoir into a hot reservoir, work must be done. So the second law of thermodynamics says that the work in this case must be non-zero. In this case, it says that QC cannot be zero, or in other words, that the absolute value QC is greater than zero. This one right here, the work in cannot be zero. Okay, so these are two statements of the second law of thermodynamics. There is a third statement of the second law of thermodynamics, and it has to do with the orderliness or disorderliness of the system and all systems which interact with it. Before we go to that third statement, though, why would these be impossible? Well, essentially, if we look at the heat engine, for it to be perfectly efficient, or in other words, for all of the heat pulled from the reservoir to be converted into work rather than having some of it dumped into a cold reservoir, would require that we have perfect control of every molecule involved in this process. And we don't. We can't have perfect control of individual molecules. Essentially, your heat can be converted into sort of organized work. So macroscopically, everything is moving together from one place to another. And then also random internal energy of all the molecules involved. And this random motion of all these molecules involved is something we cannot control. And ultimately, when you have something like friction between two objects, it converts from orderly energy, from mechanical energy, macroscopically, to more disorderly random motion internal energy. And so you're losing some amount of work from your system, and then that ends up being heat that gets transferred to your cold reservoir or your environment. Okay, so there's no free lunch, if you will. You cannot get work just from heat and not have some heat lost into the environment. No process allows for perfect conversion of heat energy or thermal energy into work. And the refrigerator statement is basically this, but in reverse. You can't recover all the energy that you have lost into the environment and put it back into the hot reservoir, because if you could, then that would essentially mean that you could then reconvert that lost energy into work if you were doing it without doing any work on the system. It basically mean that you could continuously cycle from the cold reservoir back into the hot reservoir without doing any work, and so your wasted energy from this first version would be able to be moved back into the hot reservoir and then converted back into work, and eventually you'd be able to convert all of the heat into work. And so that would be a violation of this first statement. Ergo, the two are equivalent. So what about this third statement, this disorderliness? So we have this concept called entropy, which is basically it measures how orderly or disorderly is our system. So entropy is your quantitative measurement of disorder. The more entropy you have, the more disordered your system is. Now, the entropy statement of the second law states that for any natural process, there will be an entropy increase for all systems collectively taking part. It means you can decrease entropy in one system, but you have to do that at the cost of increasing it in some other system. And if the process is irreversible, then that increase in the second system is greater than the decrease in the first system. There are reversible processes, but they sort of require very little change in entropy in one system or the other, and everything kind of happens in thermal equilibrium. Put differently, entropy is always increasing in the universe. The universe being the collection of all possible systems. So any process that is naturally occurring in the universe causes an increase ultimately in the universe's entropy. And that is the entropy statement, or the third statement, of the second law of thermodynamics. Now, in a future set of videos, I may revisit these ideas and give a better definition for entropy and maybe a little bit more of a definition for the efficiency of an engine. The point of today's video was simply to explain the three statements of the thermodynamics second law. So, thanks for watching, and I hope you enjoyed this video and learned something from it.